So today in this lecture, we are going to discuss about binary isomorphous phase diagrams. And I already introduced this one phase diagram in my yesterday topic where we have discussed Gibbs phase rule, that is degree of freedom is equal to C minus B plus 2. That is the case if you are dealing with unary phase diagram. If you have binary phase diagram, in that case, we consider your pressure is constant. So in that case, your equation gives phase rule become F is equal to C minus B plus 1. Okay. So today, like is mentioned, binary isomorphous phase diagram. Binary means there are two components involved. It means two elements you mix, then these phase diagrams will form. Like we have a copper, nickel, aluminum, gold, and any combinations. Two binary combinations. Okay. Iron, carbon. Okay. Niobium, silicon, like this you can take. So, but the word isomorphous make it distinct from other phase diagrams. Isomorphous also means like they look same in all directions, means compositionally. So I can say they are also known as solid solution phase diagrams. Also, they are solid solutions basically. So when you mix these so the element when they mix, you cannot identify. They behave like a solutions. Like we have a liquid solution, gas solution. Same way we have solutions in solid also. Now, as I mentioned, isomorphous means two component system. So there is a complete solubility in liquid. So when they are in liquid state, when melt state, so automatically at atomistic level, you cannot identify their atoms. It means they are completely miscible. In solid also they're completely miscible. So that's why we name them solid solution systems. So about solid solution, I have already discussed, I think, in defects. So where I have given talk about Hume, Rothery rules also. There are four rules, empirical rules I have mentioned in that my lecture. So today also we'll discuss somewhat that one on Hume Rothery. The Hume Rothery, the alloy systems like which one which is following home Rothery rules, okay, completely. So they basically form solid solution, and in full periodic table we have, I think, about three uh, uh, three solid solutions. One is copper nickel, one is silver gold, one is germanium and silicon. Okay, germanium and silicon. So now what statement I have written here in blue color, that is expect Tm is here is a melting point of solution to lie in between Tm of two pure component. What it means, like I suppose I'm taking copper and nickel, so they have their respective melting point. If you mix them, their alloys will have melting point in between that range only. So copper has 1085 degrees Celsius melting point, and nickel has 1435 degrees Celsius melting point. So if you make their solutions, you make copper and alloy, you make copper and nickel alloy. So their melting point will vary from 1085 to 1435 in that range only. Okay, it should not be more than nickel and should not be less than copper. Okay, the melting point that is we are expecting. Okay, so it should happen. So that's why I written if I'm taking phase diagrams is like that y-axis when I'm talking about binary phase diagram. Okay, so your pressure is here is constant, 1 atmosphere we consider. Okay, textile length. So I mentioned Gibbs phase rule is F equal to C minus P plus 1. C is the number component and how many phases are involved during the alloy preparation, that is P. And pressure, okay, pressure we are taking considering 1 atmosphere. Okay. Now here y-axis, so it means when you plot the graph, y-axis we take temperature, x-axis we take composition. Okay. So this copper nickel output. So this is a composition x-axis. So left hand side you have pure copper. It means nickel is 0%. That's why I written 0. Nickel is 0. So you start adding nickel in weight percent. So generally in phase diagrams, we take composition either in atom percent or in phase percent, weight percent or in atom percent. So you start adding nickel 1%, 2%, 3%, 4%, 10%, 20%, 30%, 50%. Ultimately, you have end up where all copper atoms are replaced by nickel. Basically, what is solution doing? Your copper atoms are getting replaced by nickel. So all copper ultimately have end up with nickel 0 copper. Okay, so right hand side means copper is 0, nickel is 100%. Left hand side you have a copper is 100%, nickel is 0. So this is my alloy composition, and there are two axes. So uh, this is temperature y-axis in degrees Celsius. So sometimes they write left axis y-axis for temperature degrees Celsius, right? They use in Kelvin, and sometimes in phase diagram bottom score they use weight percent, and above they will use atom percent. Okay, so they will use here is atom percent nickel. Okay, like this. Sometimes they use follow in this arrow. They use. So in all like all parameters, like they can put in phase diagram. Now here also I drawn this line. I could have drawn later, but it's okay. So we copper has melting point 1085 degrees. What it means melting point? Below this your material is solid. Above this material is copper is liquid. So below this it is basically solid. Above this temperature it is completely liquid. And nickel has melting point for 1453 degrees Celsius. I mean, I think I mentioned 35, 1435. That is nearly close, but I didn't remember the exact value. So exact is 1453 degrees Celsius. So below this here material is solid, liquid, and above this is liquid. Now you're making a alloy. You are making a alloy. Suppose I have made a alloy where I have taken copper 50%, nickel 50%. So this is alloy composition I have taken. So this alloy composition is basically corresponds to copper 50% nickel. Okay, I have mixed this one and made a alloy, prepared alloy. Now question comes, at what temperature this alloy should melt? So I mentioned above line, as per that line, the melting point of this alloy should have in between 1085 degrees Celsius to 1453 degrees Celsius. Since this is average composition, that we take it out the average melting point, निकालो. So that is 1085 plus 1453. Okay, that will gives me 8. Okay, 8 and 5, 3, 4, 5. Okay, I'm correct. I made it properly. Okay, 5, 3, 8, 8, 5, 13, 5, and 2. Divide by 2. So this one becomes 1, 2, 6, 9. 6, 9. So the degree Celsius. It means this alloy should melt at 1269 degrees Celsius. So that melting point is here. This one is basically 1269. Okay. But when we experimentally we melted this alloy, okay, so we came to know that alloys start melting, okay, at lower temperature here. It means it start melting before this average temperature. Like I can say 1200 degrees Celsius or 1150, it start melting. Okay. And the complete alloy melted. So this is the basically start of melting. Okay. So I can write as, so basically after this point, below this point is solid, above that is liquid, has a liquefaction starting. And liquefaction, it doesn't change immediately. You keep on heating and ultimately liquefaction stop here above this temperature. So this is my here above this one is basically completely liquid material. It means for this alloy, experimentally when they observed the melting is melting started well below this blue line and above that blue line. So it means similarly they observe experimentally for other alloy compositions also. So it means we doesn't have the fixed alloy composition. So fixed melting point for the alloy. Sorry. That's the reason we say pure metals has a fixed melting point where alloys doesn't have the fixed melting point because they are mixture. So mixture will start melting. They will not change immediately into liquid. So it will take time. So they will start liquefaction and then because copper may start melting early, but nickel will take time because nickel has a more melting point. So mixture will take time. So that's the reason for alloy composition, you don't have a fixed melting point. In place of that, your shapes of melting point and with composition, if you see, it looks like this. The shapes look like this. This is like a lens shape. And below. So this is my actual phase diagram. The blue color is not my phase diagram. So this one basically, so we have a boundary here. Okay. So below that we have a solid. Below we have a solid, and this solid is basically a mixture of copper, which is FCC, nickel, which is also FCC. Okay. So this is again a solid. It's a mixture. So I cannot say this is a pure copper, pure nickel. So I'll give a new name. This one. So this is basically this is a Greek name generally we give alpha. Alpha I cannot type here, so I'm writing alpha solid solution. Oh, okay, solid solution. And this solid solution also have crystal structure of FCC because both element has structure FCC. So alpha solid solution. Then above this we have a liquid. So this boundary, okay. So this boundary which is separating this alpha solid solution. So in between, before that, so in between basically you end up with a region. This is the region we have liquid plus solid. So this region, which is this boundary between green color, red color, this is a boundary between them. This we have a two-phase region. So liquid plus solid. So if you remember, so liquid is a single phase. Above we have a single phase. Below also we have a single phase, that is solid. But in middle these boundaries we have a double phases. One is liquid, one is solid. Okay. So let me clear this one and we'll continue. This way I have already explained. Now, what is the criteria for the formation of the isomorphous phase diagram? Why we have a solid solutions? So Professor W. Numero 3 has given some empirical rules that I have already discussed also. I'll put those 4 rules here also. What he says, you will have a solid solutions if both the element which you are going to mix have the same crystal structure. Like in copper nickel case, copper is FCC, nickel also FCC. So they have the same crystal structure. Their atomic size difference between like copper nickel we're taking, or here is copper nickel, should be less than 15%. So if you measure value, I'll show a table here. Okay. Next. So R is the atomic distance, is very close copper nickel here. Atomic size. There is a less difference in electron negativity value. Okay, that is 1.98, 1.8. And they have the same valency also, outermost cell. So if this for empirical rules, why I'm saying empirical? Because there are some special cases they can be violated. Okay. So in general, they are okay. Okay, so we can use them. So based on this empirical rule, we can say if any alloy system following these four rules, that will form a solid solution. So in whole periodic table, you metallurgy studies, they then came up with only there are three alloy systems: silver and gold, copper and nickel, and this one, silicon and germanium. Okay. So it means when you mix all these elements in these alloy systems, like in copper nickel, so they are soluble in all proportions. It means nickel will dissolve in copper, and copper will dissolve in nickel automatically. So you cannot identify their atoms in the solution. Basically, they will mix matter atom to identify हो जाएंगे EDX से, energy dispersion spectroscopy से, which one is nickel, which one is copper. Although difficulty will be there, but you can identify atoms. But they appears to us is solid solutions. So this is the isomorphous phase diagram, copper nickel. This was I have drawn just before that. I mentioned the mixture we call is alpha. Alpha is a FCC solid solution because my copper and nickel, this is alloy. And this is my two-phase region, liquid plus alpha. Solid also I can write. So the boundary which is separating this two-phase region, liquid plus alpha, from liquid, that is called liquidus. And the boundary which is separating alpha solid solution from the two-phase region, that is we call it is a solidus. Always remember these names, liquidus and solidus. Okay. So now question comes, what are the information what we learned from this phase diagram? The first thing is I am learning how many phases are present, what is their composition, what is their amount of phases, phase fraction. So we'll see one by one. So this solidus liquidus I have already mentioned. Okay, above liquidus, your alloy is completely liquid. Below solidus, alloy completely solid. Okay, so any point you take here, like I'm taking for this alloy composition 20. So my solidification, liquefaction will start this point from here. If you continue, liquefaction will stop. Your material is completely liquid. So this point. So this is my start of liquefaction, and it is completely changed into liquid. This is reverse way. Reverse way. Above point is start of solidification. When you coming down, when you solidifying basically. When you solidifying, you coming down. So this is the first cutoff point which in liquidus boundary, that is my solidification will start. And the point where it is ending, where solidus is intersecting, that point is we call it a solidification will stop. Means material is completely changed into solid. Will not stop. Okay, completely change into solid. Now we'll see effect of temperature and composition. Is there any effect of temperature and composition? So we'll take this phase diagram I already put. So if you see this point A and B, okay. Now, and this is suppose I have made a alloy, draw kar lete. I made a alloy roughly 25% nickel. I have added in copper and melted. So this is my alloy composition. Okay. So at a position, what is my temperature? Temperature is for this is 1085. Okay, 1085 only. Okay. So 1085 the melting point of copper, but is not the melting point of this alloy composition. For this alloy composition, melting doesn't start it. So material is basically solid, that is alpha solid solution. So alloy composition I have taken in here is copper, 25% nickel. So this one, for this alloy at 1085, your material is solid. At B point, for this alloy composition, roughly around 1420 degrees Celsius, so your material is liquid. Okay. So at 1200 degrees Celsius, your material is in two-phase region. You have a liquid plus solid. So I can say with change in temperature, I may end up with different phase. Okay. I can end up with a different phase by changing temperature. So this is the effect of temperature, and let's see what is the effect of composition. So if I have changed my composition from here to 80% पे ले आता हूँ, this is my alloy composition. 80%. So what will happen? My starting of melting point, what is starting? It is starting melting point, starting of melting. Sorry, copper nickel start melting at 1350 degrees Celsius. Where it is start melting with what temperature? 1180 degrees Celsius. तो मेरा जो melting point है, we change in composition, I have changed melting point of alloy. Okay, and start melting here, and it will stop. It will change into liquid at this temperature, 12, 14, 20. Okay, so it means it is remain in liquid solid state from 1000 degrees Celsius to up to what degree Celsius for 1350. Up to that is remain solid. Beyond that, it start liquefaction will start, and liquefaction stop 1220. Above that is completely liquid. So you can see clearly for phase diagram is giving information. If you change compositions, your temperature also for different phases will change. Your melting will change. Where solidification start, solidification and liquefaction start, liquefaction and so all these temperature corresponding temperature also change. Okay, and up to what temperature solid phase is stable, up to what temperature liquid is stable. Okay, so all these information, this is the effect of, we can see clearly temperature and composition. So I have already this one explained, so I'll just now come to one thing. Now suppose I have taken a alloy composition, and we know what is the temperature and the alloy composition, but we want to know at that temperature how many phases will present for that composition. So this situation is like this. I have a alloy composition. I have taken, let's take this one. So temperature is I have taken 1225 degrees Celsius, and the alloy composition is C0 38% nickel. It means in copper I have added 30% nickel. So copper is how much? 70% copper, 30% weight percent nickel. So number of phases at 1225 will be how many? So this point is falls in the intersection of this isotherm and this one, sorry, this vertical line and this vertical line, where the cross section is there. So that is a point. So this point is falls between the two phase region. It means at 1225 degrees Celsius, you will be in two phase region. One, it is a mixture of solid and liquid. So at below 1050 degrees Celsius, 1050 degrees Celsius for that alloy is basically, it will be only solid. Okay, and above 1400 degrees Celsius, it is completely liquid. So you can say how many phases. So at 1050 it is only one phase, 1225 degrees Celsius is two phase, and 1400 it is again one phase. So this is I'm getting information. Okay. Same way for alloy composition is saying composition I have changed 68% and 68% nickel, and the alloy temperature is 1150 degrees Celsius. In that case, your point is lying in solid solution, alpha solid solution. So it's saying in that, so it is a single phase. That phase is alpha solid solution. Okay, B point. Now, if we know the T and node, so we can identify how many phases are present, but also we can predict, not predict, we can determine, measure the composition of each phase. Like if it is in previous case we have seen at 1225 it is lying in two phase region. So but in that it is a mixture of liquid and solid. So now if we want to determine how much solid, what is the composition of solid, what is the composition of liquid, liquid में कितना निकल है या solid में कितना निकल है और कितना copper है. So that also how we can determine, that is rule 2. We will discuss this one. So that is we use tie line here. Okay. So suppose I have taken a alloy composition which I melted, copper 50% and nickel 50%. So I have taken this alloy composition. And at one temperature, I put 3 points A, B, D. Now, and this composition, the alloy composition generally represented by C naught. So at A point, the temperature is roughly at A point, temperature is what? Roughly I can say 1230, no, 1430 degrees Celsius. So at A point, your material is completely liquid. Okay. So this is liquid. So liquid composition will be same like alloy composition. So A point पे तो वही हो गया तुम्हारा. Okay. So A composition will be what? Your liquid composition. This will equivalent to your liquid composition that sometimes represented by Cl also. Not all the time. Cl. Okay. We write C in subscript. We write L, and तो subscript यहाँ लिखा नहीं जाएगा. So that is equal to C naught. The alloy composition. Okay, because there is only liquid, so the complete, so this Cl will be how much? Copper 50, nickel 50. Now B point, here is a catch, because it's in two phase region. One is liquid, one is solid. So your C naught we cannot take. So and that temperature, like in B, this is TA, they are written, and this one is at this temperature, B point temperature, this one 1300 something. Okay, 1225. Now at 1225, I have drawn a line which is intersecting liquidus and solidus. From there, I drawn the dotted line which is intersecting my x-axis. Okay. So that line which I have drawn from liquidus, okay, that represents the alloy composition. This is a tie line blue color, which is intersecting these boundaries. So alloy composition which is I have drawn from liquidus to x-axis, that is gives me the composition of liquid, how much liquid composition is there. And the line which I have drawn from solidus to which is intersecting x-axis, that is composition of alpha solid phase and C node. So like this, I can for different alloy composition, like for same temperature, for this course, मुझे यहाँ निकालने कितना liquid है कितना नहीं. Okay, so this is my alloy composition. Okay, and at 1150 I want to know what is my liquid composition, what is my solid composition. Okay. So this is my C node. So this is my liquid composition. This is my solid composition. Like this, the composition यहाँ दिख जाएगी कितनी है मेरी. इस roughly liquid how much? Copper 10%, nickel. Here is here roughly. So this is I can say this one is okay 25 degrees Celsius. Let's say. So this one is uh, copper 25%, nickel in solid. So if you see here, my Cl is how much? Cl is copper 40 weight percent nickel, and alpha is copper 60% weight percent nickel. So what you are seeing here uh, in solid, which is solidifying, because nickel is the highest melting point. So which when is solidifying, nickel will solidify first, because copper will solidify below. So just remember here, nickel has melting point 1435 for 53 degrees Celsius. Copper has 1085 degrees Celsius. Now when it cooling down, so which will atom start freezing first? Nickel. So that's why. So that's the reason. The in solid, uh, if you compare, the solid will have more nickel compare with the liquid case. So that's the reason. So copper here, here C alpha has composition Cu 60 weight% nickel, and liquid composition is Cu 40% weight nickel, and C naught is 50% malachite composition. So at any temperature, at any composition, you can identify what is my phase composition. Now, what is D point? D point is again end up within solid. So in solid, में तो फिर this is again alpha TD. So that is 1129. So at D point, you have again your solid composition is completely correspond to your C node. That is 58% nickel. This single phase. So this is this way how using tie line I can predict into phase region. Tie line we use into phase region. Otherwise single phase with कोई issue नहीं है that. Because liquid composition also equivalent to C node and solid composition also equivalent to C node. Problem only comes when you are into phase region. So there we draw a tie line at that temperature on which temperature you want to measure the composition. Okay. So I hope this one is clear. कोई doubt है तो पूछ लो, because based on this definitely there will problem, numerical problem will come in exam. Okay. So a tie line is constructed across the two phase region at the temperature of alloy. Okay. Now another rule I am discussing here is lever rule. Now we know the composition. What is the composition of liquid? What is the composition of solid? Means copper, nickel, how much they are in its respective phases. But now, what is the amount of fraction of liquid and what is the fraction of solid? Composition कितना fraction कितना? In that two phase region at that temperature मेरे पे 40% liquid और 60% solid है. Or I can say 60% solid or 40% liquid. So this is also fraction. Sometimes we write in percent for like this also. Sometimes we put in fraction also 0.4 or 0.6. Okay, 0.4, 0.6 gives me 1 like this. So their lever rule we has given, and this is a mass balance kind of rule. Like we have तराजू होता है ना, उसमें measure करते हैं आप लोग. So it's like that we have a perculum. One end I put one mass, another end put one mass. So suppose left hand I put mass of liquid, another I put left hand side, right hand side put mass of alpha. And from perculum their distance in R and S respectively. So their phase fraction निकालना है. So here perculum is represented by the like in this is a phase diagram and two phase region. Blue color had drawn, and this B point which is correspond to C node, that is behave like a perculum here. Okay, so one side you have a Cl that is can correspond to Ml. One side you have a C alpha that is correspond to M alpha. Okay, so same way, and this is distance from C node to Cl is R, and C alpha S is C alpha minus C node. So I can write R is C node minus Cl, S is C alpha minus C naught. So for Coulomb, what is this formula? Mass fraction by represented by, so if liquid mass fraction represent करते Wn and Wa for respective phases. So liquid की composition mass fraction निकालना, so Wl is equal to ml upon total mass, ml plus m alpha, or in distance if you know in terms s upon r plus s. But अगर phase diagram के term में देखना है, s is what? S is c alpha minus c naught, and r plus s is means c alpha minus cl. So this is my phase fraction of liquid into phase region at some particular temperature. Okay, so C alpha minus C naught and C alpha minus CL. अगर W alpha निकालना है, that will be R upon R plus S. So that will be C naught minus CL divided by C alpha minus CL. That will give me the composition of, no, not composition, sorry, phase fraction of solid. So WL plus W alpha is equal to 1 always. अगर परसेंटेज लिखना तो 100% लिख सकते हो. Like we have a C naught, this alloy composition, C naught 35.8% nickel. So from phase diagram we know that the alloy composition from correspond to C alpha is 42.58% nickel and Cl is 31.58% nickel. So WL I have to calculate. So this is C naught minus C alpha निकालना है पहले तो, that is C naught minus Cl divided by C alpha minus Cl निकाल लो, ये आ गया 0.68. That is liquid and solid ही आ गया 0.32. अगर इन दोनों को ऐड करोगे तो ये फेज फ्रैक्शन है, it is equal to 1. So I can write W alpha plus WL is equal to 1. If I know one phase fraction, I can calculate the other one. Just 1 minus 0.68 gave me 0.32. If I know 0.32, so which phase fraction of liquid will be 0.68. Also 1 minus 0.32 give me 0.68. Okay. So same way you can do this one in terms of volume fraction also of the phases. So basically volume fraction is like you have design alloy, and in that alloy you have some regions correspond to alpha phase, correspond to region is correspond to beta phase. So measure the volume of alpha phase, measure the volume of beta phase. Okay. Now in that case V alpha correspond to the volume fraction of alpha, and beta is the weight fraction. Beta is the weight fraction of, sorry, volume fraction of beta. So V alpha is equal to V alpha upon V alpha plus V beta. निकाल सकते हो. And V alpha plus V beta is equal to 1. So V beta is equal to 1 minus V alpha. So A is phase fraction. So phase fraction volume. So or a phase volume fraction depends on the volume of alpha and beta phases. अब मैं एक आइडिया देता हूँ, टाइम है तो. So we can calculate. Like sometimes like this we get from the microstructure. You have a microstructure, in that we have a grains. Okay, so these are the grains we have. You can see the grain boundary. Okay, so for this one is correspond to alpha, this correspond to beta, again alpha, beta, alpha, alpha, alpha. So now what you do, you measure this area, this rectangle area, measure this length and this length. So this one gives me, this is 2D way basically, 3 dimension is difficult. So it will give me area fraction, not the volume fraction. So roughly if you know the thickness, you multiply by area, then you have a volume fraction also, no problem. Okay, so but that can be equivalent, you can measure, that can be kind of equivalent we take. So V alpha plus V beta will basically comes from this area, total area, and then V alpha you measure, सबका area निकालो, area of this grain, alpha के जितने भी हैं. All alpha you measure this grain. ఇంటి ఏరియా నికాల్. Measure this area. Alpha. Measure this area. So this is basically V alpha. Then put in this formula. Then V beta आप automatically निकाल सकते हो. V alpha plus V beta is equal to 1. So V alpha we find out, V beta we can find out. So from microstructure we can find out the volume fractions. Okay. So I'll stop here because the topic is next one is how the microstructure get developed. I cannot complete within 5 minutes that topic, so we'll start this one tomorrow and finish. So up to isomorphous phase diagram that I'll finish tomorrow lecture. That will be the part of your quiz too. Okay, defect, corrosion, and till isomorphous phase diagram will, which I complete tomorrow, will be the part of your quiz too. Okay. So that's for today. कोई doubt हो तो पूछ सकते हो.